All right, guys, quiz should have closed out by now. Last day of April, and that was your last Friday quiz. Like I said last time, I think there's a good chance we might actually finish up a couple days early. So we'll just end up seeing how that goes. So the game plan for the rest of the day here is to introduce an application of Lewis structures. So we don't just do these things because they're fun to do. We can actually use them to solve problems. And we're going to see that a little bit further on down the line when we start talking about geometries as well. And by the way, watch the next video for Monday, which is the molecular geometry video, which is what we're going to pick up with on Monday. So what we want to talk about today is an application. And the application is this. We want to calculate an enthalpy of reaction, a delta H of reaction. So you remember that from the thermo chapter, right? So if I had, for example, standard enthalpies of formation, I could calculate a delta H of reaction by just summing up the overall enthalpies of the products and subtracting from that the overall enthalpies of the reactants. So what we want to do is use bond energies to do this. So it's an alternative way of getting at a delta H of reaction. All right, so let's look at a real simple example of this. So let's look at a simple combustion reaction. So I've got CH4 in the gaseous phase, okay? And then I'm just going to give it to you as a balanced reaction here. That can react with two oxygens in the gaseous phase. And since it's combustion, you can predict what we're going to make. We're going to get carbon dioxide gas. And we're going to get water, in this case, two waters. All right. Now, we know we can kind of predict that since we're burning something here, we predict this is going to be an exothermic reaction, right? So energy, once we get the reaction going, should be given off by this reaction. So I want to use bond energies to be able to determine if that's absolutely true. Now, here's the deal. I'm going to start with Lewis structures because if I'm talking about bond energies, what I'm really talking about here is the amount of energy it takes to break a specific kind of bond. So, for example, if I've got a chemical reaction like this, in order to get from reactant side to product side, I've got to break some bonds between carbons and hydrogens and also between oxygens, right? And then I rearrange all those atoms in a different way to make carbon dioxide and water. Okay, so I got to break a bunch of bonds first, and then I'm going to come back and form a bunch of new bonds. Okay, so bond energy is the amount of energy it takes to break a certain type of bond. So that's why we need the Lewis structure. So you guys can verify these Lewis structures as I go. CH4, I think we did that one in class a few days ago. Looks like that. Oxygen looks like this. Okay, carbon dioxide. Remember, we had several possible Lewis structures for that, and the best one, based on a formal charge argument, is that. And water we also did in class. It looks like this. And again, for practice, you guys could go back and verify all of those different Lewis structures. Okay, I'm going to go ahead and put coefficients in here to remind me of what they are. Okay. Now, here's the deal. With bond energies, we find those in tables. Okay, so we have bond energy tables that we can find in pretty much any textbook. In your particular textbook, they're found in table 7.2. Now with Chem 101, it's going to automatically link you to that, so you don't have to actually go to the textbook and find it. Or if you're working problems like this in Chem 101, it'll just give you the bond energies you need. Okay, so normally you don't really need to go look them up. Okay, so what do I mean? Well, let's just look at a couple examples of bond energies that we might find in the table. So one type of bond I could have would be, for example, a carbon-carbon bond. I don't have any of those in the example up above, but that's just a good example of one. And if I look at the bond energy that goes with it from the table, it's 345 kilojoules per mole. Look at a different carbon type of bond. You can have a carbon-carbon double bond. Now, since you got two bonding pairs there, you'd expect this bond to be a little stronger. So you might assume that it would take a larger bond energy to break it, and you'd be correct. This one's almost twice as much, 611 kilojoules per mole. So again, what am I talking about here when I talk about these bond energies? What I'm talking about is the energy required to break 1 mole of a particular type of bond. Keep in mind, these are in terms of kilojoules per mole. So we're talking about per mole of bonds here. Okay, so we'll go ahead and state that just so you know what it is. All right. So what we'd find is that some bonds are stronger than other bonds. Some bonds are weaker, and that's going to be reflected in the bond energy. Now, the other thing to keep in mind here is since we're talking about the bond energies as being tabulated as the energy required to break 1 mole of bonds, these are all going to be endothermic, right? So as we tabulate these things or find them in the tables, they're endothermic, means energy in, right? We got to put energy into the bond to break it. Now, here's the interesting thing about this. Remember, we said in a chemical reaction, I got to break a bunch of bonds. That's going to mean energy goes in, but then I got to turn around and make a bunch of new bonds. So if bond breaking takes energy, what do you think bond making is going to do for you? Well, it's an opposite process. So you'd be correct to think that we'd get energy back out, okay? So if we come back up to our equation over here, the process up here on the reactant side of breaking the bonds is going to be endothermic. But the process on the other side of the arrow of making the new bonds is going to be exothermic. So if I'm applying a bond energy to an exothermic process, I need to make sure I change the sign on it and make it negative. Okay. All right, so you can kind of see what we're going to do here. I'm basically just going to tabulate the number of bonds I got to break and then the number of bonds I got to make. And I'm going to basically do this as an accounting exercise, add them all up at the end and see what we get. All right. So looking at what I've got there, I'm going to make a little table here. So I'm going to just say I've got the number of bonds that I'm interested in here. I can put the bond energy next to it. That's going to be in kilojoules per mole. And we can kind of keep track of what we're doing here. Okay. So over to the left here, I'm going to put the type of bond that I've got. So if I come back up to my CH4, look at what I got. I got a carbon with 4 hydrogens bonded to it. So how many CH4 bonds do I have to break? Just looking at it stoichiometrically. How many of those things do I got to break per molecule? Well, I got 4 bonds, right? So that means I got to break 4 of them. So the number of bonds is going to be 4. So the type of bond is going to be the carbon-hydrogen bond here. The number of them is going to be 4. The bond energy I can go look up in the table, and that turns out to be 415 kilojoules per mole. So what do I do here to tabulate the total energy required to break them? Well, it's going to be the bond energy multiplied by the number of bonds I got to break. Okay, everybody see what I did there? Now come back to the O2. Look at the Lewis structure there. I've got an oxygen-oxygen double bond. And how many of them do I have to break? Now the stoichiometry of the reaction tells me I got to break 2 of them, right? So I've got, what did I say, an oxygen-oxygen double bond, which you can look up. I got to break a total of 2 of them. And I can look up that bond energy. It's 498 kilojoules per mole. Okay, so that's all the total bonds I got to break. Okay, so what do you think I should do? Well, I multiply those together and then add them, don't I? So collectively, if you do that, 4 times 15 added to 2 times 498 gives you 2,656 kilojoules per mole. Okay, or we could just leave it at kilojoules if we want. Okay, so that's the energy I got to put in. Okay, that's the endothermic part to break all the bonds. But now I want to come back around and form some new bonds. So I'm going to put a little divider here. So the new bonds I want to form are what? It looks like I got to form some carbon-oxygen double bonds. How many? Oh, it looks like 2 of them. Okay, so let's do that first. Okay, so I could look that type of bond up. By the way, I have 2 of them. I could look it up in the table. And it's going to be 741 kilojoules per mole. But I'm going to make it negative now because, again, what are we doing? We're forming the bond instead of breaking it. So now we have an exothermic process. We're getting energy back. Okay, what else do I have up there? I've got some oxygen-hydrogen bonds. Okay, so if I look up an individual oxygen-hydrogen bond, it's going to be minus, again, making it exothermic, 464 kilojoules per mole. How many total do I have to break? Well, it looks like I've got 2 of them per molecule, but then I got 2 molecules stoichiometrically based on the coefficient in front. So that looks like I got a total of 4 of those oxygen-hydrogen bonds I got to break. 2 per molecule times 2. So that's a total of 4, right? Multiply those together, and what am I going to get? Well, it turns out I'm going to get minus 3,338 kilojoules. Okay. So you can kind of look at this already and say, all right, who's going to win out, the positive or the negative? Well, it looks like the negative number is bigger, so the negative is actually going to win out for us. So to get the delta H of reaction, what do? I'm just going to add those guys up, okay? It's kind of like Hess's law, if you remember Hess's law. All right, so when I add those 2 things up, I'm going to get minus 682 kilojoules per mole. And that's per mole of reaction, right? So what do we get here? We get an overall exothermic reaction. And that makes sense, as we said, because if we look back above, it's a combustion reaction. So we'd expect to get heat or energy back out of it, and indeed we do. So again, this is just a demonstration of another way in which we can calculate the delta H of reaction. That's a little different from what we learned back in the thermo chapter by using delta H as a formation. Okay, and again, you got to have Lewis structures. You got to have a balanced chemical reaction equation, but you also have to have Lewis structures so you know what kinds of bonds you're breaking and making. All right, any questions about that, guys? Everybody okay? All right, so what I'd like to do with the balance of the time that we have is I want to go back to Chem 101 and I want to do a little bit more advanced practice with some of these Lewis structures, okay? Because it's sort of important to what we're doing here in terms of this material we just talked about, but it's also important from the perspective of where we're going, which is going to be dealing with molecular geometries. In other words, you got to have a Lewis structure before you can get a molecular geometry. Okay, and ultimately, that's going to build into properties of molecules that we want to talk about. Okay, so formal charge and exceptions. Let's start this one. You got 20 minutes, and that's about the amount of time in class we got left. Maybe 15, but you'll get well into it. Okay, so there it is. And some of these are really similar to some of the quiz questions. Some of them might even be the same questions. I'm not sure. Was the first one in the quiz? It might have been. I think that was on the quiz. So everybody should get that one right. Look familiar.
Is it possible that you could go over number 6 on the quiz?
Yeah, we can swing back around a little bit later and look at it. I'm just going to give folks a little time to get into this, and we can swing back around. You'll have to tell me what the number 6 one is because it varies by person.
Okay.
I mean, I can swing back to the quiz. Yeah, why don't I head back there now? And while you guys, some of you guys can work on this, we can go back to number 6. How's that? Practice.
The one with selenium, oxygen, and fluoride.
Yeah, okay. So let me see. Do you have it in front of you? You can tell me what it asked for. I mean, I could go to the quiz. All right, which one was this?
It says determine the valence electrons and then draw the structure.
Yeah, the selenium oxygen with the 2 fluorines, and we want to, I'm going to just do it and then we'll just show the question. Okay, so here's what it is. All right, so that's what we got. Unfortunately, I'm working off one screen today instead of 2, so I can't really project this 2 places. So we want to determine the number of valence electrons on it. So let's just do that. Okay, so selenium is coming in with how many? So you need a periodic table, right? So you'd find the group
6.
number, 6, good. Oxygen's coming in with how many?
6.
That's 12, right? And then fluorine, you got 2 of those. So you've got 12 plus 2 fluorines, right? Fluorine is what, 24? Or sorry, it's 7. Twice 7 is 14, right? And we had to add 12 to that. Am I right? Doing this in my head.
Yeah.
So that's what, 26?
Yeah.
Okay. Yeah, like I said, I can't write it down. I'm just doing it. Okay, so we got 26 valence electrons to play with, and then we're supposed to draw the Lewis structure. So let's see if we can do that. What was it? SeOF2. So who goes in the middle, do you think?
Se.
Se. Yeah, that sounds good. So let's go ahead and just assign that since we're here. Okay. And how many bonds do I have to really take out to it? How many things is it bonded to?
3 things.
Okay, so we'll go ahead and put our 3 bonds out there. All right, so now what do we got? We got to go ahead and say, okay, we got an oxygen here, so I'll make this an oxygen, right? And I got 2 fluorines, right? So I'm going to make that guy a fluorine. Where's fluorine? There it is. And we'll make this guy a fluorine. Okay, so let's do that. All right, so we got everybody, right? So now what I'm going to do is I'm going to turn around to the chalkboard and I'm going to kind of work through this because, like I said, I don't really like to mess with it on Chem 101. I like to scratch it out first and make sure I know what I'm doing before I start actually putting electrons around everything. So I'm going to put the selenium up here. I'm going to put an oxygen over one side, fluorine on one side, fluorine on one side. And then what does the rule say? It says make the bonds, which we've kind of already done here. So I've got 1, 2, 3, 4, 5, 6 electrons to make the bonds as you see them. Okay. So now the question becomes, all right, where do I go next with the electrons? I go to the outer atoms, right? Okay, so let's see here. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 around the fluorine. 13, 14, 15, 16, 17, 18 around the oxygen, 19, 20, 21, 22, 23, 24 around the fluorine so far. And then it looks like I've got an extra pair that would go on the selenium. Now, is this the one? Let me just run backwards. Is this the one that says to apply the octet rule to all the atoms? I have to go back and look. Is again, I can't go backwards. What is the original problem asking me to do? Just, do I need to minimize formal charges or just put an octet around everything?
Then follow octet rule.
Follow the octet rule. Okay, so what that tells me is that everything has to have an octet around it, right? Using all 26 electrons. So it's not telling you to minimize formal charge or do anything like that. It's just telling you to get an octet around everything, right? So I think I've actually satisfied that requirement on the board here. So if I do that, let's go ahead and put the electrons around the fluorines here. That look right? I think that's right. Let's go to that fluorine, do the same thing. Okay, then I'm going to do the same thing on the oxygen. I want to just take a quick electron count here and make sure I didn't miscount anything. 1, 2, 3, 4, 5, 6, 7, 8. 3 times 8 is 24, right? So we need one more pair, don't we? And once we've gone around the central or gone around the outer atoms, where do we go next?
The center.
Center. Got one more to do. So I'm going to click on the selenium and I'm going to put a pair of electrons on the selenium. Now, this isn't necessarily the best Lewis structure, but this is satisfying the requirements of the problem, right? Problem said, make sure everybody gets an octet. Okay, so let's see if that's what we did. There it is. And what is it like? It tells them I didn't write the right structure. What is the right one? Your submission, what did I not do? Looks like the same thing to me. Oh, I know my problem. I didn't tell it how many valence electrons. That's the issue. I got the right Lewis structure, but I didn't tell it the right number of valence electrons. I think you have to choose that in there. That was the problem. So wherever we do that. Boom, sorry, I missed that part. So you have to choose, it's got 26 valence electrons and we got the right structure, so now we're good. Okay, does that answer the question for you?
Yeah, I think I just missed the octet rule part of the question.
Yeah, and you got to watch that because Chem 101 from time to time will actually ask you that. It'll tell you to either minimize formal charges or it'll tell you to apply the octet rule to all the atoms. So you kind of have to watch the fine print there. All right, I'm going to pop back and see how folks are doing with the homework here. Or with the class practice, as it were. Okay, so far so good. And you can see with like a lot of these ones here in the practice, it's asking you to minimize formal charge. Oh, there's an incomplete octet. I think that BF3 one, I think we did in class last time. Number 3 here is a lot like the one you just asked about. It says that you want to follow the octet rule on all atoms, so you don't necessarily end up with the best possible structure, formal charge wise. But again, watch the fine print there, guys. All right, we're down to about a minute or two of class. So I just want to recap a couple things for Monday. Keep in mind that we will do a 5 for 5 on Monday, and that all the 5 for 5s we get from here on out are extra. So try to rack up as many of those as you possibly can. Also, make sure you're watching the next video, which deals with VSEPR and molecular geometry. So we want to make sure we get that under our belts, because that's what we're going to talk about and focus on Monday. Any final questions, guys? All right, then. Everybody have a great weekend, and I will see you on Monday.
Professor, I had a question.
Sure, go ahead.
I looked over my Chem 101 and I'm
Yeah.
missing, and I was not able to attend